Okay, so this is where we left off. This is chapter 3 again. We were discussing about the points where the function is not differentiable. You are seeing actually three types that you can observe by looking at the graph of the function. For example, we've seen a corner example. For example, absolute value of x has a corner at 0. Actually, if you remember, by using the limit definition of the derivative, we had seen that the limits one-sided limits, they differ. So the corner situation happens when we have the one-sided derivatives differ. Okay. So this is one first type. Another type is cusp. Okay. This is if you look at the slope of the secant lines, okay, it's p. Let's approach from the left. Look at this secant line. Okay, this secant line, and then this secant line, this secant line. So as you would see that the slope is increasing very, and it's getting very big as we get close to p from the left. All right, and then so the slope at p from the left becomes infinite. And let's get the slope from the right, slope of the secant line. This is negative, this is negative, and this is negative, smaller and smaller. So these negative values gets close to negative infinity from the right hand side. So this is going to cause a cusp. Okay, it's going to be seen like this usually. Look at that. Okay, there's a big difference between this and this. Okay, so in other words, you have infinite derivatives, infinite slopes on either side. For example, for this one, positive infinity slope, negative infinity slope, you can say. Okay, of course, approach to that value, approaching to plus infinity and negative infinity, right? And there's another situation where we have the vertical tangent line. For the vertical tangent line, we are interested in the point P, and let's get the slope of the secant lines that are getting close to P, right? This is 1. Okay, this has a negative slope, but these slopes are getting negative still, but getting bigger. Okay, and then if you look at here, so these are approaching to negative slope, negative infinity. The slope is approaching to negative infinity, and look at this. This slope is negative, 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 and the slopes are getting to negative infinity as well. Okay, so vertical tangent line occurs if where the slope of PQ approaches plus infinity from both sides or approaches negative infinity from both sides here. So there's a difference between a cusp and vertical tangent line. Here, the slopes, they differ. One-sided slopes have the opposite signs for the infinite values, but here the slopes, one-sided slopes, if you look at, they have the same sign. For example, left slopes of the secant lines approach to negative infinity, right slopes of the secant lines are also approaching to negative infinity. Okay, that's the difference. So this is infinity, negative infinity, negative infinity. Here, positive infinity, negative infinity. For here, on the other hand, look at the P and look at the tangent lines to the curve. Here's the Q, and these are getting closer and closer to P. Alright, and the slope is positive and getting bigger. And let's get this one. So this is the first secant line, second secant line, third secant line. These are all negative, and one-sided derivatives, they differ. The derivatives here, they are finite, like the slopes, one-sided slopes are finite. Here, one-sided slopes, they are infinite, and with opposite signs. Here, one-sided slopes, they are infinite and they have the same sign. Okay, that's the difference. So corner, cusp, and vertical tangent line you can have. Okay. So sometimes, of course, these are what other types of discontinuity types we do have. We have the let's say the function is discontinuous at a point. If the function is discontinuous at a point, it is automatically not differentiable at this point. Look, at this point P, there's a jump. So blue graph comes in here and then jumps to here to continue, right? So this function is definitely discontinuous. Okay, and now look at the slopes of the secant line. Look at this. Look at this line. The slope is positive, and then here positive, positive, but getting steeper, getting bigger. Okay, so this slope can never be equal to this slope, because this is a negative slope, by the way, and it's a positive slope. And this shows that, I mean, whenever we have jump discontinuity like that, if there any type of discontinuity there, forget differentiability at that point. Here's another example, and about discontinuity. Look at this curve, and at this point there is a jump right here. Okay, and if you start drawing these secant lines from that point to here, look at that. These are all positive and getting bigger and bigger on the left side, and on the right side they are getting smaller and smaller, negative but. Okay, so in that sense never equal to each other. Because of that, no differentiable at P. How about oscillation or oscillation? Either way you can hear. They call it wild oscillation. This is a very well-known example. Y is equal to x sine 1 over x whenever x is never 0, but it's going to be 0 when x is equal to 0. Okay, so how should we understand this? So we are interested in the derivative at 0, right? Let's get the right secant lines. So pick any point from the curve and combine it with P. You get the secant lines, and then, alright, and as you see, the slopes are all sorts. Like this one is, let's say, maybe 1. This one is maybe 6 over 7, etc. This is smaller. These are negative ones. Okay, so there are some negative ones, there are some positive ones, so there are no way that you will be able to get a right slope. Okay, and similarly from the left. So there's this, because of this wild oscillation, you never expect, even if this is a continuous function, look at this, but you will never see the derivative at this point. Okay. This theorem is important. This theorem tells you that differentiability is stronger than continuity. So if a function is differentiable, then it's going to be automatically continuous, but not vice versa. So if a function is continuous, that would not always mean that that function is differentiable. Sometimes it's differentiable, sometimes it's not, depending on the function. Theorem 1 says if f has a derivative at x is equal to c, then f is definitely continuous at that point c. Okay, that's what it says. Alright. Differentiation rules. Okay, so we are going to be seeing standard facts or results or properties of the derivative. First of all, when you have a constant function, you have just a constant function like that, then the derivative is going to be 0 because there's no change in the function. It's all the same, all the time the same. So because of that, the derivative is going to be 0. If you don't believe me, then you can use the definition of the derivative, put it in, and you're going to see it. Okay. Here's actually a proof to get that x and x plus h. This is the first point. This is the second point image. Okay. F of x is c. F of x plus h is c. C minus c. F of x plus h minus f of x is going to be c minus c, which is 0 on top over h. 0 over h is 0. So this is true. If you have a positive integer power, then the derivative, whenever n is a positive integer, then the derivative is n times x to the n minus 1. We can prove it if you want to. I'm not going to do that, but that's true. There's a power rule. This power rule, the previous one is also a power rule, but it is for integers now. This one is for any real. Okay, then for any real, okay, as long as x to the n and x to the n minus 1 are defined, for any real, the derivative is going to be n times x to the n minus 1. Okay, derivative constant multiple rule. So let's say we have the function u and we have a constant c, and then c times u is a new function. And if you want to take the derivative of this, it is the same as c times du dx. So c, you don't do anything to c in here if c is in front of u. Okay. So there are some examples here with the powers. Y is equal to x squared is a power function. The derivative is 2x. Y is equal to 3x squared is a power function. The derivative of this is going to be 6x actually, and then the value of the slope at that point is 6 times 1, 6, and the value of the slope at the point 1, 1 is 2 times 1 is 2. Okay, so next rule is the derivative sum rule. If you have two functions that are differentiable at x, and their sum is going to be differentiable at every point where u and v are both differentiable, at x values that they are both differentiable at such points, we will be able to write the derivative of u plus v is going to be the derivative of u with respect to x plus the derivative of v with respect to x. This d over dx is a Leibniz, a famous mathematician, has this notation. He had found this notation, d over dx notation. So whenever we have this in front of a function, we should understand that it is the derivative of that function with respect to the variable x. Okay. Okay, so let's look at this curve. This is a blue curve that we look at, and then we have this red horizontal line. These horizontal lines are tangent lines to the curve. For example, this horizontal tangent line is a tangent line at -1. This is a tangent line at 0. This is a tangent line at 1. Okay, so as you see, we have this horizontal tangent line whenever the curve has some sort of minimum here. Do you see that? There's a minimum of this curve right around here, and maybe there's a maximum right here. So we have this horizontal tangent line, and again we have a local minimum at 1. Local minimum means, I mean, locally this takes the minimum value around it. Okay, so we have a horizontal tangent line at that point. Okay, it's good to know we have this horizontal tangent line. Okay, derivative product rule. What is this? Let's say u and v are differentiable functions at x. Their product is going to be differentiable as well, u times v. And how are we going to take the derivative of that at that particular point x? The derivative is going to be you keep the first one as it is, take the derivative of the second, plus take the derivative of the first times keep the second as it is, second function as it is. So that's the rule, that's the product rule. Okay, and then we have the quotient rule. If you have two differentiable functions u and v at x, and we assume that v is never 0 at this particular point x, then the quotient, which is u over v, is differentiable at x. And there's a rule for that, of course. These rules, all of these rules are coming from this limit definition of the derivative, okay? But we don't prove it, we just say it, because proving it is going to take a lot of time, so we don't prove it. But you should believe me that these formulas that are quotient rule, product rule, sum rule, all of these guys are coming from the limit definition of the derivative. So the derivative of the quotient of these two functions is take the derivative of the, okay, we have here we have the numerator and the denominator. Take the derivative of the numerator, keep the denominator as it is, minus keep the numerator as it is, times take the derivative of the denominator with respect to x, and then all over take the square of the denominator. Okay, that's the rule for the quotient, derivative of the quotient. Okay, in section 3.4 we have if you look at the derivative as a rate of change. Okay, if you remember in chapter 2 we just mentioned a little bit of average velocity, the average speed. Average speed would be just this part. Okay, this part would be the average speed. And if you take the limit as h goes to 0, you get the instantaneous velocity like that. Okay? Similarly, we are going to look at this as rate of change of f, and then we let limits h goes to 0, and we are going to call this instantaneous rate of change of f. So it's just a general version of this average velocity and instantaneous velocity. Okay? So that's the definition. So the derivative of f at x0, which is the instantaneous rate of change of f with respect to x at the point x0, is just the limit of this quotient. Okay? Of course, here we assume, as always, the limit exists. What happens if the limit doesn't exist? Then it's undefined, right? Instantaneous rate of change will be undefined. Okay. Let's say there is a body that's moving along a coordinate line. Okay, and let's say this function f with respect to the time t, so as t changes, the position of the object is changing. So s shows the position of the body, okay, of the object, and then at time t, the object is in here, and after delta t seconds or minutes, whatever the unit for the time is, okay, the position of the body is going to be here. Okay, so this delta s is going to be the distance, the displacement. So how far did this body moved after delta t minutes. All right. Okay, so this picture is good. So is again position at time t is f of t. Position at time t plus delta t after delta t minutes. The position is s plus delta s, which is f of t plus delta t. Actually, this delta s is the displacement. So initially it was s, and then we add delta s displacement, and this is the new position of the body. Okay. This type of pictures are useful. You're going to see that. Okay, so I talked to you about the velocity, which is the instantaneous velocity we mean. It is the same as limit of that quotient. Okay, see, we are just doing t plus delta h minus f of t over delta h, delta t. So here delta t goes to 0. This is like instead of h, we use delta t because we want to show, because velocity depends on time, right? Instead of using h, we wanted to say t, delta t, so that it is much more clear. So velocity, which is the instantaneous velocity, is the derivative of the position. F is the position function. It's the derivative of the position. S is the position, which is f of t. Actually, we could write df dt here with respect to time. And velocity is shown as v of t. Okay. So body's position at time t is s is equal to f of t, right? This is the initial position, you can say, is initial position. And about that body's or that object's velocity at time t is, you just use this function, form the ratio, the quotient, and then take the limit as delta t goes to 0, the time difference goes to 0, then you're going to get the s dt. Okay, instantaneous velocity. All right. Okay. Now we want to understand the meaning of the derivatives a little bit more. So let's say s is equal to f of t, and this is the what? A position function, right? So let's say, so this curve, as you see, it's an increasing, going up, right? It is increasing. And what does it mean? The displacement is increasing, right? You are changing the position. Okay, so that's gonna tell you that rate of change. Okay, let's go back to here. Okay, and you will be able to change the position. Your position will increase. Okay, if you have a velocity, right? If your instantaneous velocity is positive, if your velocity is positive, so ds dt, which is the velocity, is positive. If you have a speed, then you're going to continue to change the position. If your velocity is 0, you won't be able to do that. So therefore, the velocity has to be greater or equal to 0. But what's the velocity? It is ds dt. Okay? So ds dt is at the same time, it's the limit of that quotient, which is actually, it is the slope of the tangent line. So slope of the tangent line has to be positive. So if the tangent line has a positive slope, that would mean that velocity is positive, and you're going to continue to have displacement. All right, positive slope, so moving upward. Okay. If there's a negative slope, which means velocity is negative, what does it mean, velocity? Velocity is negative, you are moving in the opposite direction, right? So therefore, displacement is decreasing as position is going to be excuse me, my phone. Let me turn it up. Okay. Okay. DST velocity is negative and it's going in the opposite direction, so S is decreasing, displacement is decreasing, your position is decreasing, right? So we have the graph has negative slope, okay? So you are moving downward, okay? So in summary, if you have the motion, which is represented by s equal to f of t along a straight line, okay, you can consider this as vertical axis, okay? So because moving up and down we say, right? So let's look at it like that. So that's why it's written moving up or down. If you have velocity positive, then you're moving up. If your velocity is negative, that will mean you're moving downward. You're moving in the opposite direction. So we have this, our straight line is this vertical axis, okay? Okay. So S is going to increase when dSdt is positive. S is going to decrease when dSdt is negative. Okay. So let's look at the speed. So what is velocity? What is speed? Velocity is a speed that is a direction. Speed, just a number. Speed doesn't have a direction. Okay? And it's going to be either 0 or positive, but velocity could be negative as well, because negative in front of the negative velocity means you're moving in the opposite direction, so it shows you the direction. So speed is going to be actually the absolute value of the velocity at time t. But what is velocity? Velocity is the dSdt, right? Change in the position, rate of change in position. Okay, let's see. Okay, here, this is about a question, but I am trying to tell you. So first of all, this graph is about, it has two axes, one t, which is in terms of second, and vertical axis, the horizontal axis is time t in terms of second, and the vertical axis is v in terms of the velocity, okay? And so there's a moving object, so let's try to understand. So here, okay, the speed is, for example, here the speed is constant, okay? The v is constant. The v is constant means you are moving, still v is constant and v is greater than 0, it's not 0, so you are moving forward still, okay, but with a constant speed. However, here the speed is increasing, okay, so speed is increasing, so it is positive. It was 0 here, but it's increasing, so you are moving forward, okay, because v is positive. And then here the speed is going down, okay, that means you are slowing down, okay, but you are still moving forward. All right, so let's say v is negative, so between 3 and 4, and actually 3 and 5, the v is negative. But look at that, v is negative means you are still moving. However, your speed is increasing. Speed is increasing because absolute value of the velocity. However, you are moving in the opposite direction, okay? Alright, here v is negative, you are moving backward, okay? You're speeding up, look, because speed is absolute value of v. So let's say this is negative 10, the speed is 10. Here, negative 5, the speed is 5. So you are speeding up. But if the graph is like this, then look, velocity is still negative, which means you are still moving backward, but you are slowing down, okay? Because, for example, here your speed was 10, here velocity is negative 5, but absolute value is 5, your speed is 5. so you are slowing down here. Okay, and then at 5, what happens? The velocity becomes 0. What does it mean? The object, or you driving the car, let's say, you stopped, and between for 1 second, your speed is 0. Okay, you stand still, you cannot move anywhere, no forward, no backward. And then what happens? And then your velocity is positive again. You are moving in the direction that you started with. Okay, let's say at the beginning you were moving towards east, then now you're moving towards east. Here you are moving towards the opposite, west, here on this area. And then velocity is greater than 0, you are moving forward again. You're speeding it up. It was 0, speed was 0, then it came up to here, speeding up in 1 second. Okay, that's how you should understand the graph. Okay, then we have another notion. So far we have the position function, s is equal to f of t, and we have the velocity, which is v, which is equal to ds dt, and we have an acceleration. So acceleration is what? It is the derivative of velocity now with respect to time. So as I told you, s is equal to f of t. It shows the position at time t. Then, of course, the body can speed up, and we need to find out how much it speeds up. So we take the derivative one more time, rate of change of the derivative. Rate of change of the velocity, which is the derivative of the velocity at time t, is going to be the acceleration. Actually, this is the same as twice derivative of position function s. Okay, you take the derivative of s twice to get the acceleration, but you take the derivative of velocity once to get the acceleration. And then we have one more. So we have position function, we have velocity function, we have acceleration function, and we have jerk. Jerk is the derivative of the acceleration with respect to time. So it's the third time derivative of s, but first time derivative of acceleration is the jerk. Okay. So let's say we are at top of a building, okay, and then we have a ball in hand, and we drop this ball, and the ball, of course, because of the gravity, it's gonna go down. Initially no speed, okay. In 1 second it just drops down 5. In 2 seconds it just drops down 20 meters. In 3 seconds it just drops down 45, in total 45 meters. So it's interesting. So there should be some sort of a mathematical formula that shows this relationship, okay? And there is actually. Okay, so here's one example. This is the rock in example 4. You don't need to know the details about this. Probably they are dropping. I'm trying to. Probably you are throwing up. You are throwing the rock. It goes high up and then goes down. Okay, that's what it is. Because of this graph, I can understand that. So there's a rock, you are here, your position is at 0, and then you throw the rock, and then it's gonna go until the speed is 0. Look, it's gonna go high, 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 and then of course as it goes up, the velocity is gonna drop down, and at the very high, which is the maximum position in the air, this velocity will be 0. If it's not 0, then it's going to go further up. Okay, when it's 0, the velocity is 0, it will tend to go down. Okay, the question was probably at what time t it's going to be in the height 250 feet. That's the question, I believe. Okay. What is given? We are given the position function s is 160t minus 16t squared. Alright, so and then this is the s function, and in the v function, v is the yellow color. Okay. Let's first understand the blue one. So at the beginning, the position is 0, and then it has a velocity 160 meter or feet per second, I guess. What's the feet per second, I guess, yeah. At the beginning, the rock has the velocity 160 velocity, and it's gonna go down. It's gonna be 0 after 5 seconds, and then last 5 seconds it's gonna come back to you, okay, with the same velocity but in the negative direction. Look, negative 160 degree is 160 feet per second. Okay, this is when you throw the ball, you give it its initial velocity, because otherwise it's not gonna go up. Okay, initial velocity is 160, and then after 5 seconds it's going to stop. The velocity is gonna be equal to 0, and then it's gonna start coming down. When it's coming down, the velocity is gonna get higher, but since it's in the opposite direction, we have the negative in the front, and after 5 seconds it's gonna be 160 feet per second, but in the opposite direction. That's why we have the negative. So the yellow one is the velocity graph, and blue one is the distance or position function. Okay, and then you should be aware that the rock is going to have the maximum position in the air as max when velocity is 0. But what is velocity? ds dt is equal to 0. So you're going to take this, you're going to take the derivative with respect to t, which you did here. The derivative of s with respect to t is 160t, 60 minus 32t, and if you equate this to 0, you get 160 over 32 is going to be the time. So we are interested in, what is this? If you divide 160 by 32, you're going to get 5 times. 5 times 2 is 10, 15, 16. So 5 times 32 is 160. So that's why actually after 5 seconds the velocity is over. Velocity is 0. That's how we find it. We just took the derivative, equate this to 0, and we get the time t equals to 5 seconds. And afterwards we draw our picture. Okay? Another question could be, how do I know that initial speed was 160? Actually, it is obvious why. The velocity is the derivative of this, right? Just put t is equal to 0, at time t is equal to 0, 160. Okay, that's what you get is that. And if you're interested in what is the velocity after 10 seconds, because after 5 seconds it is 0. After 10 seconds, 160 minus 320 is going to give you negative 160 feet per second. So we have everything in here coming only from this formula. We start with the position function, we take the derivative, we equate it to 0, and we get the time it takes to reach the highest level, and then and we want to find out the initial velocity. So we have the velocity formula, we put t is equal to 0, we get the 160 as the initial velocity, and we want to find the final velocity after it drops down, and it takes 10 seconds. So we put 10, we get negative 160. We already know it, but we are double checking every work we had. Okay, that's the example 4 in the book. Alright, so this is about a steel production. They produce steel weekly, and this graph shows you there's x-axis and y-axis. X-axis shows the weeks, and y-axis shows let me see, no, x shows, okay, the production per week, Okay, how much tons per week. So x, here x is tons per week, and yx is the cost, how much a week the production. Cx is the cost of the production, so this is cx. Okay, cost of the production. So for example, to produce x tons per week, the cost will be this much money. To produce x plus h tons per week, the cost will be higher because you're producing more. And then the slope is called the marginal cost. These are economics terms, and as engineers, actually, you should get familiar with it. You're going to be learning it in economics class that you are expected to take during your years here. Okay. Usually they ask you to find a marginal cost, which is actually the derivative of c with respect to x, and you guys know you just take the derivative of c with respect to x. Okay. And the marginal cost, which is dc dx, is approximately the extra cost delta c of producing delta x 1 norm unit. So if you produce 1 tons per week, it's going to approximately extra cost delta c, and this is called the marginal cost. Okay, per each unit of production, how much it's going to cost you is the marginal cost. Okay, here you are given a graph which is y is equal to 2p minus p squared, and then here's the derivative of that p, and the derivative of this is 2 minus 2p, which we got here, 2 minus 2p. This is a line, but line with a negative slope, therefore we drew it like this. I think this is about a problem, example 7 in the book, and probably this graph tells you the proportion of smooth-skinned peas in the next generation. It shows the proportion. If the proportion is 1, then so yeah, maybe we don't need to really, p should be proportion. Y is how much you're gonna get in the next generation or something. Okay, and then this is derivative as well. Derivatives of trigonometric functions.